So today we are going to have an idea of the Gaussian quadrature theory. Okay, so this we all know that the degree of precision for any n plus 1 point quadrature formula k lies between n and 2n plus 2. Okay, so now Gauss wondered if it is possible to make a proper choice of the nodes x0, x1, x2, xn such that the degree of precision becomes exactly equals to just the one less of it, that is 2n plus 1. Okay, and he gave forward the theorem this as a necessary sufficient criteria for this one. Key the degree of precision for an n plus 1 coin quadrature formula will be exactly equal to 2n plus 1. So how is that possible? Is given by this theorem. What the theorem is stating, it is saying a necessary sufficient condition for an n plus 1 point quadrature formula with node set to x0, x1, x2, xn to have degree of precision 2n plus 1 is this. That is what it is, the definite integral of omega x and multiplied with qnx dx must be equal to 0, where qnx is an arbitrary polynomial of degree less than equal to n. That means of degree at most equal to n. So if this is true, then whatever n plus 1 point quadrature formula you are taking with the node point set to this array of elements x0, x1, x2, xn, then the 2n plus 1 will be the degree of precision of that quadrature formula. Okay, and vice versa. If I set any quadrature formula, n plus 1 point quadrature formula with the nodes this one, then it will have such that this is true, then it will have a degree of precision 2n plus 1. Okay, so I'm not going into the proof of this theorem because it is not related to the C programming we have to develop here. Only for the sake of knowledge, I just discuss the result here. And the one thing which we want to take here from the as an extract is that this Qn polynomial, which is ultimately he has said this arbitrary polynomial ultimately takes the form of the Legendre polynomial. Okay, with the suitable transformation of these xi points. Okay, the suitable transformation is given by this x is given suitable transformed by a plus b by 2 plus b minus a by 2 into t, where t is a parameter. Obviously, if you discretize it, then xi and ti will be coming, and a is the lower limit of the definite integral, which we have to calculate, and it is the upper limit of the definite integral. So if you want give this type of translation, and then if we follow the standard method of doing this, then ultimately we are getting key this Legendre polynomial will be coming in the form of this, or this Qn will be coming in the form of this Legendre polynomial. Okay, so if I say n is an n plus 1 point quadrature formula, so we will be dealing with a Legendre polynomial of the parameter n. Okay, so that is something related to this theorem. We are not going into that part. What we are just trying to just shape or just use as a formula in our programming is this. First, we have a look at the weighted quadrature formula. Okay, so in obviously we know we have to deal with sometimes with this type of definite integral where wx multiplied with fx we have to integrate within the range a and b, where omega x is a, it's not omega x, sorry, my mistake, wx, it is a weight function, is a given non-negative. Okay, non-negative, as it is a weight function, so non-negative function called the weight function, which is the same for all functions fx belonging to a given class. That means this function actually what happens, it differs from one quadrature formula to another. You can take it via in any non-negative function, you can take it. Okay, and in most cases what we will just now see, for our purpose we will take wx to be 1. Okay, so once you take this type of definite integral to be evaluated, then the quadrature formula, the weighted quadrature formula, the weights coming from here is given by, that means this is given numerically by this formula. What is this formula? Summation over I running from 0 to n of hin yi. What is hin? Hin is actually the Hermite polynomial, which is given by this. Okay, this is the discrete part we are just saying. Okay, where you just, if you just see the expression, it is nothing but wxi omega x by x minus xi into omega dash xi, and the error term is given in this form. Okay, so for Gauss Legendre quadrature formula, what we take, this is a specific one of this one weighted quadrature formula, where we take this weight function to be 1. Okay, so what actually we are doing, we are calculating this one, and we are making the linear transformation as we just said for the theorem also. This is the linear transformation we are making so as to transform AB range of the interval of over which we are integrating to -1 to 1, and setting xi equals to b plus a by 2 plus b minus a by 2 ti. Obviously, if I am making this transformation, then definitely if you take the nodes now, x0, x1, x2, xn, which we know we have to deal with the nodes, then the nodes get transformed into the new set of nodes ti. Okay, and wx is given by this wx here, which is required, is given by b minus a by 2 to the power n psi t, where psi t is this one, t minus t0, t0, t minus t1, t minus tn. So it is an n plus 1 degree polynomial. And as I said, this ti is nothing but the roots of the Legendre polynomial of parameter n. Previously, we have seen that ultimately the Legendre polynomial is coming into the scenario. Okay. So here, what actually for this for our purpose, just let us just focus on for our thing, that we have to perform this type of integration. Actually, we are trying to perform. If you take wx equals to 1, then what happens? Whatever function you have to evaluate, you can use that. For that in definite integration evaluation, you can use this formula. Okay, with wx equals to 1. So with that motive, we are just taking a particular case where we are taking wx equals to 1 only and making this transformation along with w small w, that is actually it is omega x, you may say. We are making this as our assumption. This and these are our assumption. These are the settings we are using here, where psi t you have to have an idea ki these are nothing but the roots of the Legendre polynomial of parameter n. Okay, so once you use this, then f of this thing, then means x is replaced by the t parameter, which can, you may say now it is a function of t, so I mark it as a new function, obviously capital Ft. Okay, so ultimately we are performing this ab fx dx integration is performed in this form, b minus a by 2 minus 1 to 1 integration over capital Ft. Okay, Achha. Now as I said, psi t is given by Cn into Pn plus 1t, where Pn is a Legendre polynomial of degree n. So you know how it is the form of this Pn, okay, and Cn is a constant given by this one, okay. So ultimately, ILG means here, as I said, I am specifically taking Legendre polynomial, okay. I am sorry, not for that. Here we are taking Legendre polynomial, one thing, and Wx we are taking here to be 1. So for that part, if you consider, then what you are getting here, you are getting this as your quadrature formula. Okay, so what is quadrature formula? If you read or see the expression, half of b minus a, okay, and then summation over kin f of ti. Okay, so kin is given by this, okay, and ti are the roots of the Legendre polynomial. Here you are taking n, okay, roots of the Legendre polynomial of degree n, then that means pn plus 1t. Okay, so this is the formula we are going to use as a Gauss quadrature formula. Okay, and so one thing is very sure ki if we have to deal with this formula, we have to have in our hands this ti, and depending on this ti, this xi will be coming and also this kin will be coming. So we need both of them to evaluate this one. Okay, and so ti you can get from the Legendre polynomial degree n, because once you know the Legendre polynomial, from there only you can calculate the roots. Okay, but in most cases, let me just specify if it is given to solve this Gauss quadrature formula while using a C programming, what they will do, they will provide you with this ti. Once these ti's are provided, also they will provide you with this ki, that is a function c ki here which is required, the constant. This ki and ti will be provided. In case it is not provided, then you have to find out the ti using this roots of the Legendre polynomial, and then kin will be performed or evaluated using this if it is not just provided. But in most cases, ki, the values of ki and ti will be provided. Okay, for example, if you just consider, so this one. Okay, so suppose compute the integral by Gauss's method, correct up to 7 significant figures by taking 5 ordinates. Okay, so here they are taking a1 and b2. So these are the upper limit and the lower limit. Xi is half into 3 plus ti. This is coming by a plus b by 2 plus b minus a by 2 into ti. Okay, like that. Just as I said here. This is the thing which you are using here. Oh, this one. Okay, this one here is used. Okay, so once you use this, you will be getting this one. That is not an issue. You will be getting this one. Okay, and what that will be provided is this ti value will be provided. Here we are working for n equal to 4, 5 for ordinates. So starting from 0, 1, 2, 3, 4, so 5. So here this ti will be provided and this kin will be provided. So once ti provided, xi is calculated by this one. Also ki can be calculated using this formula, but ki will be provided. In case not provided, you have to calculate it out. Okay, ki will be given by this formula here. Okay, but as you can see, it is not at all very trivial one, it's a tedious job. So in most of cases, they will be providing you with all this piece of information. Okay. So once this is provided, then what we have to do? Nothing. Ti, xi, from Ti directly we are getting xi. This is nothing hard to calculate. Ki will be provided, Ti provided, xi calculated, f of xi you can calculate by using the fx, whatever fx form is given. Okay. So one thing you see, the whatever fx is given is not an issue. Here I can change this function also. The main thing is that what Ti, set of Ti, how many you are taking, what are the upper limit, lower limit you are taking, because depending on that, this xi will be set up. And also the n is important, how many ordinates you are taking, because then only the Legendre polynomial roots you can calculate. Okay, so that is main important. I can replace this by any other smooth function. Okay, any other function which I am taking ki antiderivative exists. We are not going into all those analytical hazards. We are just considering this. You can just perform the integration suitably. Okay, so this and this you are getting here, and this f of xi will be you can get. So once you get this thing, then what is kin into f of xi you want to have to calculate, because according to the formula what you have to get, we have to get the summation of this kin into f of xi, this thing. This is the thing we want to calculate, and with that you have to multiply half of b minus a. So I need the summation of this one, so I have created this table here, this one. So once you find out the total, then you have to just multiply with half of b minus a. Here this 2 minus 1 means 1, so half into this part, so you are getting this one. So exactly this thing I have to just put in the C programming. The programming is very easy. Okay, actually what we are doing for our purpose, we are taking a very precise, I try to give a very precise idea of what we actually want to do with the Gauss quadrature. Here we are just concerning ourselves with the Legendre polynomial. Okay, and just keep one thing in mind about the degree of precision what they said there, though it is not exactly used here, but you have to keep that idea in your mind. And with that thing set up, with Gauss Legendre polynomial we are assuming, and with this sort of transformation we are giving, so as to just replace the definite limit of integration by minus 1 1. So ultimately you have to deal with this, you have to just calculate f of xi. This and this will be provided, this Ti, Kin will be provided. You have to find out xi, you have to find out f of xi, and then you have to multiply f of xi, Kin for each I, and then you have to add up and just follow the formula half of b minus a into summation of this. That means the total of this column. So this is the thing we have to put in the C programming. So you can just simply understand that the programming now turns out to be a very trivial one. Okay. So what we are doing here, C programming to evaluate this expression exponential x by x square, x cube minus 1. This we are taking here as a function over the interval 2.5 to 4.5 by 5 points by Gauss quadrature formula with 12 subintervals. Okay, so here you get the idea how many points you have to take. Okay, so here we are getting this, we are just giving a sub function, a auxiliary function, that is the function exponential x by x cube minus 1. Okay, and then starts the main function where this set of values will be provided, as I said, t6 and k6. Here in 5 points you just said 5 points, so here t6 6 will be given starting from 0 up to 5. So 6 t6 is placed in this array and k6 is placed in this array. Okay, and then yes, x and y we are just taking here, and some CAB, these are some of the variables which we need, we have just declared it. Okay, so what you have to ask from the user, provide the lower limit and the upper limit. Okay, as I said, it is required. So once they provide it, stored in AB. Okay, then these are the some of the things given to just we take as an output or print as an output the table as I showed in the PDF. Okay, so for that thing what you are doing, I starting from 0 to n. Okay, so I starting from 0 to n, what you have to do, we have to perform the translation. So this is the translation formula. Okay, once you perform the translation, what you have to do, you have to calculate the f of xi. So yi equal to f of xi, but xi means this thing only. Okay, so yi equal to f of x means yi equal to f of a plus b by 2 plus b minus a by 2 into ti. You already have ti in your hand, so you can easily calculate. Fx is also there in the sub function, so you can easily calculate this yi. Once you calculate the yi, what you have to do, you have to perform the multiplication for each I, ki into yi. Ki is also again provided, yi you are calculating, so c is very coming easily. So sum equals to, sum was initialized to be 0, and each time you run this loop for every I, it is increasing by this c amount. So ultimately, and what you are doing, you are printing each and every row as here, so as to create the table. you're printing each row, this one, this one, this one, this one, and this one. Okay, so for that this print is given within the loop. Okay, this already we have a fair idea about. So this one we are coming, and this ultimately what you are getting, this is the ultimate Gauss value of the integration v minus a by 2 into this whatever sum you are getting here. Okay, so the value of the integral is this one. Now here I am repeatedly saying I am not giving any specification. I leave it upon you to decide the specification depending on the accuracy which is demanded. Okay, so let us end here, and just if you just run it, let me just show. Okay, so if I suppose what was the lower limit, upper limit they demanded for. Okay, it will be given in the question only what this is demanded for, 2.5, 4.5. Okay, 2.5 and then 4.5. So this is the thing which is coming, value of the integral. Okay, here the accuracy you have to put, and you have to mention that accuracy level here. Only that thing I am not just put it here inside the program. Okay, so this is it for our purpose. You just remember the formula. Okay, we are not going to the theory part because only this programming part is required. So up to that, that formula is enough to keep in mind. Okay, and mostly this will be provided. If not provided, you know the Legendre polynomial, you know how to calculate the roots. You have to calculate the roots. That's the thing. Once you calculate the roots, you can create this table. Once you can create this table, the K6 will be coming by this table, this formula, which is given here. Okay, but I admit that this is really a tedious job to just calculate all this. This is really time consuming one. Okay, but obviously no, they will be providing with this one. Okay, so with this I end up here the Gauss quadrature formula programming. Okay, we'll stop here.